This is going to be a lesson that will deal with the properties of logarithms. Now, we've looked at logarithms and what they meant and how we went about working with them. Uh, we began with looking at exponential functions in the form of y equals b to the x. Well, we wanted to solve for x, and so we wanted to find the inverse of the function. Well, if you remember, to find inverses of functions, we switched the x and the y, and then we solve for y. But we didn't know how to solve for y any more than we knew how to solve for x. So we had logarithms, and a logarithm is going to help us do that. Now, the way that we write logarithms is in the special form. B is our base here, and y is our exponent. So we would write this as the log base b of x is equal to y. And then we can solve for y, where y is the exponent. And so we took this exponential function and wrote it in the form of a logarithm. And we're going to now look at properties that we can do with our logarithms. But the purpose of a logarithm was to be able to solve for an exponent. And so from our exponential function, we found the inverse of it. And then a logarithm is the inverse of an exponential function. So let's look at some properties that we have with logarithms. The first one that we're going to look at is called the product. The product rule. Now, in this, remember, when we took a log of a number, that number was always a positive number. So if we're going to take the log base b of a product of m times n, now in this, what I was meaning was that m is greater than 0 and n is greater than 0. And neither of them equal 1. We're not talking about the log of 1. So our product rule says the log of a product is equal to the sum of the logs. Now this should make sense because if you remember, a logarithm equals the exponent. And when you multiply like bases, you add your exponents. So the log of a product is equal to the product of the logs. That should be an n there. And I always try to say it in the way that I just did. The log of a product is equal to the sum of the individual logs. So if we were wanting log base 6 of 5 times 7, this would be equal to log base 6 of 5 plus log base 6 of 7. If we had the log of 10x, well, this is the log of 10 plus the log of x. Now, in an earlier lesson, we looked at some properties of when the base of the log was the same as the base of the number. And this was what we called our common log. When we write no base, it's understood to be base 10 because that's our number system. So the log of the base of the log is the same as our number that we're taking the log of. So this was equal to 1. So 1 plus log x. And we've simplified it in a little way. If we had the log of 100x, well, that's the log of 100 plus the log of x. Now, we could write 100 as 10 squared. And the base of our log is the same as the base of our number, so it's equal to the exponent. So this would be 2 plus log x. And so these go back to some of those basic properties of logarithms that we looked at in the last lesson. And we can then use that to do some simplification. So that's our product rule. In the product rule, the log of a product is equal to the sums of the logs. Okay, we want to look at the next rule, which is our quotient rule. And again, we're talking where m is going to be greater than 0 and n is greater than 0. Now our quotient rule is dealing when we're taking the log of a quotient. And again, this is a positive number. Both of these are positive numbers. So the log of a quotient is equal to the difference of the two logs. Again, this should make sense because a logarithm equals the exponent. When you divide like bases, you subtract the exponents. And so the log of a quotient is equal to the difference of the two logs. Now this is where our base is not 1. Because again, we're looking at those same properties that we dealt with our logs to begin with. Back when we were defining our logarithms, we defined this that m and n would always be greater than 0. They would be positive numbers, and that our base could not be 1, and that our base would be a positive number. So that just dealt with when we were taking logs of how we can take logs of numbers. So besides stating here that m has to be greater than 0 and n has to be greater than 0, we'll also state that b cannot equal 1. Just going back with what types of numbers we can take logs of. So if we were going to deal with this, then we could say the log base 3 of 5 divided by 7 would be the same as the log base 3 of 5 minus the log base 3 of 7. This is called expanding our logarithm, and so that we can deal with it in different ways. If we had the natural log of e squared over 4. Well, the log of a quotient is equal to the difference of the logs. So that would be the natural log of e squared minus the natural log of 4. Well, the natural log is base e, so the base of our log is the same as the base of our number, so this would be equal to the exponent minus the natural log of 4. And so we can do some simplification with these. The third rule that we have with our logarithms is called the power rule. Which deals when we raise to powers. Again, m is greater than 0, n is greater than 0. So the log base b of m raised to a power, we'll just call it p, raised to the power p. Now let's think back with our exponent rules, because logarithms are equal to exponents. When you raise to powers, you multiply the exponents. So this is going to be equal to the power times the log. So if we have log base 6 of r squared, then this would be equal to 2 log base 6 of r. It's equal to the power times the log. We try to never have this written as a product or to a power or as a quotient. We'll simplify it down using these rules. If we had the natural log of the square root of x, well, another way of writing the square root would be x to the 1/2. So using our power rule, this would be equal to 1/2 the natural log of x. If we had log base 5 of x minus 4 cubed, this would be equal to 3 times the log base 5 of x minus 4. Now, one of the things you need to be careful of, we don't have a rule for subtraction or addition. This is considered to be one factor. That's why it was in parentheses. It's one number. So we can't break it up into more than one term. So we would keep it then in parentheses. Now what we want to do is learn how to expand our logarithms and then how to condense them. And we used to do this a lot of times to do computations. We don't actually need that anymore because we can do the computations on a calculator. But some of the processes that we use in solving problems, we still need to be able to expand or to condense. And so even though we're not going to do this to actually use logarithms and use log tables to do computations, we still need to understand the processes of expanding or condensing our logarithms. So let's go through and let's look at expanding them. Let's say that we've got the natural log of e to the 4th divided by 8. Okay, what we want to do is to write this as the sums and differences of individual logarithms where we have no exponents, we have no addition, no multiplication, and no division. So we look at this. This is a quotient. So we're going to expand it. The log of a quotient is equal to the difference of the log. So we would start out, that would be the natural log of e to the 4th. But we don't want to put an exponent. The log of a power is equal to the power times the log. So we would write that as 4 log e minus the natural log of 8. Now we can do some simplifying because the natural log of e is 1. So we have 4 times 1, which is 4, minus the natural log of 8. And we could have also gotten that just by saying, okay, the base of the log is the same as the base of the number, so it equals the exponent. Let's say that we've got the log base b of x squared times y. So now what we're taking is the log of a product. The log of a product is equal to the sums of the logs. So this would be log base b of x, but we don't want to put an exponent, x squared, so that's the log of a power, so that's the power times the log, plus log base b of y. So we had the log of a product, that's equal to the sum of the individual logs. Here we had the log of a power, so that's the power times the log. Log base b of x cubed times y divided by z squared. Okay, we've got a product, we have a quotient. Well, we have to think back to our order of operations. Our order of operations say that we'll do the numerator, we'll do the denominator, then last of all, we'll do the division. So we're going to consider this then, it's going to be the log of the product minus, for the division, the log of the denominator. So we're going to have log base b of x cubed, that's the log of a power, so that's the power times the log, plus log base b of y, then that's divided by, so minus log base b of z squared, which would be the power times the log. Now, you could think of it as this is understood to be in parentheses. So we could have put parentheses around this part, But since it's the beginning, if we remove them, we would have the same thing. Now, if it were in the denominator, let's just take this same problem, log base b of z squared over x cubed y. Here the parentheses become very important. So I'm just going to go ahead and put parentheses around this denominator because it will be very important as we go through. So this is going to be equal to the log base b of z squared, which will be a power times the log. And that was just the way that I learned to do it, was to go ahead and write it, and when you get to where you want to put an exponent, then it's going to be the exponent times the log. And I learned to do this before calculators, when all of this was necessary to do my computations. Okay, then minus, and then I'm going to put parentheses because we're now dealing with the log of a product, but it was in the denominator. So minus log base b of x cubed, which would be the power times the log, plus log base b of y. Now when we go through and we remove these parentheses, then our signs are going to change. Log base b of x minus log base b of y. So it's important when you've got a product in the denominator that you recognize that it's in parentheses. It's not so necessary when it's in the numerator because that was a positive in front of our parentheses anyhow, so when we removed them, nothing was going to change. Okay, let's look at one that looks pretty involved. Let's say that we have the natural log of x to the fourth times the square root of x squared plus 3 over x plus 3 to the fifth. Now you may want to rewrite this to begin with as the natural log, and you could rewrite it as you wrote down your problem, x to the fourth times, and make this x squared plus 3 to the 1/2. You don't have to, because you can recognize that taking the square root's the same as raising to the 1/2 power. But we do have to deal with our fractional exponents. Now we cannot remove these parentheses around the x plus 3 because all of that's being raised to the 5th power. We can't remove it around the x squared plus 3 because all of that we're taking the square root of. So when we expand this, we've got a product in our numerator, and then we do the division. So we would have the natural log of x to the fourth, which would be 4 times the natural log, plus the natural log of, in parentheses, x squared plus 3 to the 1/2 power, which would be the power times the log, minus the natural log, in parentheses, x plus 3 to the 5th power, which would be the power times the log. And so this is expanding our logarithms. And if you'll just say your rules as you go through, it's not so bad. The log of a product is equal to the sums of the logs. The log of a quotient is equal to the difference of the logs. And the log of a power is equal to the power times the log. Now, the other thing that we need to be able to do is to condense our logarithms and write it back as a single log. When you've got the sums of two logs, or the difference of two logs, or power times a log, there's times that you need to write it back as a single log. And so that's what we're going to look at next. And it's going to be important then that we can write these back as one log. And we'll do this probably in working our problems. We will take an expanded log and write it back as a single log more often than we will actually expand. Well, to condense them, It's just doing everything backwards. If you've got the sum of two logs, log base b of m plus log base b of n, the sum of two logs is equal to the log of the product. If you've got the difference of two logs, log base b of m minus log base b of n. Now the bases had to be the same, so the difference of two logs is equal to the log of the quotient. And if you have the a power times a log, then that's the same as the log of something raised to a power. So it's the same rules, it's just doing them backwards. And so you've got to know these frontwards and backwards. So let's look at some examples of those. If we have the log of 7x plus 6 minus the log of x. Now I wanted to do one here for you to recognize we're not talking about the log of a sum. We don't have a rule that deals with the log of a sum. So we can't break that up. We have to keep it in parentheses. What we're dealing with here is the difference of two logs. So the difference of two logs is the same as the log of the quotient. So 7x plus 6 divided by x. If we have 4 natural log x plus 7 natural log y minus 3 natural log z. Now again, we deal with our order of operations. So our order of operations say we would be adding before we would subtract. We go from left to right, so we'd do our addition, then our subtraction. So you could think of this as in parentheses, which means we've got the sum of two logs, which is the same as the log of a product. So what we're going to do is we're going to write down log one time. That's how we know when we've condensed it, when we've got it written as one log. So this would be the product, so that would be x. Now notice it was a power times the log, so that's x to the fourth times, here we've got a power times the log, y to the seventh. Now we'll deal with the subtraction, which would be the quotient, so divided by z cubed. Again, it was a power times the log. But you deal with your order of operations, which says that we were going to be multiplying these before we did the division. All right, let's take this one, 1/3 parentheses log base 4 of x minus log base 4 of y. Now what these parentheses mean is that all of that was being raised to a power. So it's not just this first one that we were raising to a power, but both of them. So if we can go back, let's deal with what's in the parentheses first. It's the difference of two logs, so that would be the log of a quotient, x divided by y, and all of that was being raised to the power. So the cube root of that quotient. And if you wanted to, you could write this as log base 4 of the cube root of x divided by y. But that's what it means when it puts your difference inside parentheses, then it means that whatever that was, if it was a quotient or if that had been a plus, the product, both of those are being raised to the power. So if we have 1/2 parentheses log base 5 of x plus log base 5 of y minus 2 log base 5 of x plus 1. Again, I want you to notice the difference here. Here we're doing the sum of two logs. Here we're doing the log of a sum. That's two different things. This does not deal at all with any rule that we have. Here, this is one quantity that we have to remember that we keep it as one quantity. So we've got our sum first. So that means that we're doing log base 5 of our product, xy, but both of those were being raised to the power. So that would be to the 1/2 power or the square root of that, divided by, because it's minus, x plus 1 squared. Now, if you have trouble remembering it this way, what you can do is you can say, well, let me distribute that 1/2. So it's 1/2 log base 5 of x plus 1/2 log base 5 of y minus 2 log base 5 of x plus 1. Then if we dealt with it, we have log base 5 of x to the 1/2 y to the 1/2 over x plus 1 squared. And we do have a rule back with our exponents that if you've got, you're multiplying these and you're taking the same root, which that would be the square root of x times the square root of y, that's equal to the square root of xy. So we still get the same thing because up here it was the product that we were taking the square root of, which is what we're saying here. So if you have trouble remembering, then go ahead and do your simplification, distribute that 1/2, and then you can raise each one of them to the 1/2 power. Okay, let's say we've got log of x plus the log of x squared plus 4 minus, let's make that a minus 4, minus log of 15 minus log of x plus 2. Okay, as we go through this and think of our order of operations, this is saying that we're doing our multiplication, and we would do that first. Then we're going to do division, and then we're going to do division. Well, that doesn't make a lot of sense to say we're going to divide and we're going to divide. So right here at the start of our division here, then what we're dividing by, if we factor out our negative and put this in parentheses, we're dividing by a product. So when you've got more than one term after that minus sign, then you need to factor out your negative so that, and put it in parentheses so that you know what you're dividing by. So we can write this as log of x times x squared minus 4 divided by 15 times x plus 2. Because it's the sum of logs and it's the log of a product. So there are times when you've got the minus there, then that lets you know that you're starting your division and you need to see, well, what all are you dividing it by? And it makes it just a little bit easier to go through. All right, that's called condensing, writing it back as a single log. And you know that you've got it back as a single log when you've only written the word log down one time. As long as you've got logs written more than once, it's an expanded form. Okay, one of the things, the last thing that we want to look at in this lesson is dealing with some of our logarithms and how we go about evaluating them. And so if we wanted to do some evaluating and with our different logs, there's a process that we go through. Let's say we've got log base 14 of 87.5 equals y. This is what we want to evaluate. So we're going to say equals, we don't know, equals y. Well, in this form, we don't know how to evaluate this because it's base 14. Even your calculator will not do this in this form. Your calculator only works in base 10, the common log, and base e, the natural log. It does not work in base 14. So we need to do some work with this. Well, let's write this back in exponential form. So that would be 14 to the y is equal to 87.5. Now we have an important property that we're going to use here, and that deals, and we've looked at it a little bit before, but the property says that the log base b of m equals the log base b of n if and only if m equals n. If you have two numbers that are equal, then the logs of those numbers will be equal. The same thing, if you have two logs that are equal, then that means those two numbers are equal. So here we have two numbers that are equal. 14 to the y equals 87.5. So that means the log of both sides are equal. So if I took the log of this side, and I can make it any base that I want. Well, the only two bases we can work with are base 10 or base e. So if I did it in base 10, then the log of 14 to the y is the power times the log is equal to the log base 10 of 87.5. Now if I wanted to solve for y, I can divide both sides by the log of 14. So I get that y is equal to the log of 87.5 divided by the log of 14. Now I can go to my calculator and work this because these are in base 10. So let me just erase this, and then we're going to pull up the calculator and look at how to use the calculator to work these. Okay, let's use our calculator then to evaluate this. Now, since we made these into common logs, then we're going to use our log button here. So we would say log of 87.5 divided by log of 14. And we're going to round these off to 3 decimal places. So we'll round it off at this point. So this would end up being that our exponent y was equal to 1.694, or 1 and 694 thousandths. So that's saying if we took 14 and we raised it to the 1.694, we would get 87.5. Well, let's just try that. If we took, we said 14, and we raised it to the 1.694. Now, it may not turn out exactly because we rounded off. Then we got 87.405. If we had carried that out to more decimal places, we would have been a little bit more accurate, but we're pretty accurate. So logarithms help us solve for exponents. That's why they are so important. It's one of our only ways that we have of solving for exponents. Now, we did that in the common log. We could have just as easily taken the natural log of that. So let's take that same problem, and instead of it being the common log, let's do the natural log. So the natural log of 87.5 divided by the natural log of 14 and we got the exact same answer. So it doesn't matter what base you change it to, you're going to be able to get the same answer. Now, since the only two bases that we know how to do computations for are common logs or natural logs, then we want to do that. And most of the time, we're going to change it to the natural log because there are some problems that we can only work in natural log. And so we can do all of our problems if we change it to natural log. We can do some of our problems when we change it to common logs. So I get in the habit of always changing it to the natural log. So what we're doing then, this is called our change of base. And our change of base simply says this. If we've got log base b of m, and we can't work in that base, this is the same as log base a of m divided by log base a of b. It's the log of our number divided by the log of our base. If you look back up on this one, we had the log of our number divided by the log of our base. And it just depends upon what base you want to change it to. You had to change it to the same. So we're either changing it to the common log, so we would do the log of m divided by the log of the base, or we're going to change it to the natural log. And as I said, most of the time, this is what we'll do. We'll change it to the natural log. Okay, let's look at one more where we're doing our change of base. Okay, let's take the problem, the log base 3/10 of 19. Now, if we use our change of base formula, then that's going to be the log of the number, and I'm going to use natural logs, the log of the number divided by the log of the base. Well, if we go to our calculator, and let me make that a little bit smaller where we can see it, see our problem also. Okay, that's going to be the natural log of 19 divided by the natural log of 0.3, or 3/10. So that turns out to be negative 2.446. So that's going to be negative 2.446. And again, if you forget this change of base formula, it's okay. Go back to that property that we were talking about. I think it was on a different page here. Maybe not. The property that dealt with that if you're trying to change a log and you can't find it, write it back in exponential form. So this would be 3/10 to the y equals 19. If you have two numbers that are equal, then their logs are equal. So this would be the natural log of 3/10 to the y, which would be y times that, is equal to the natural log of 19. If two numbers are equal, then their logarithms equal. Then when we solve for y, we can divide. And this is where we get our change of base formula. And so that would be the same thing there. So if you forget your change of base formula, then you go back and you think of that rule that if two numbers are equal, and it's if and only if their logs equal. Okay, so what we've looked at is the product rule, which tells us that the log of a product is equal to the sums of the logs. We looked at the quotient rule that tells us the log of a quotient is equal to the difference of the logs. We looked at the power rule, which says the log of a power is the power times the log. Then we used those rules to do some expanding. We also dealt with if we had a logarithm that was expanded, then we could write it back as a single log, and that was called condensing. And we wanted to write it back where we only had the log written once. Then we looked at changing bases because we can only work in base 10 and base E. So if you have any other base, then you have to change your base. Well, that's equal then the log of the number divided by the log of the base. And most of the time we will want to write it using the natural logs because there are some problems that we can only work in natural logs. So we can always work in natural logs. We're limited in working with common logs.